Thermal expansion. Expansion of solids. Increase of volume due to increase of temperature is called expansion. Depending on the geometry of the object, three types of expansion can be defined. Linear expansion. If only the length of an object is significant, as in the case of a rod or a string, then the relationship for expansion can be expressed as in following equation. Here L naught is the initial length, L is the final length, theta is the temperature difference, alpha is called the linear expansivity. If we subject alpha from the above expression, alpha can be written as this. As per this expression, linear expansivity alpha can be defined as the fractional change of length per unit change of temperature. SI units of alpha is per Kelvin. It's a dimensionless quantity. If only the area of an object is significant, as in the case of a thin sheet of metal, then area expansion can be expressed as in following equation. Here in this equation, A naught is the initial area, A is the final area, theta is the temperature difference, beta is called the area expansivity. According to this expression, beta can be written as this. Therefore, beta can be defined as the fractional change of area per unit change of temperature. SI units of beta also per Kelvin. It's also a dimensionless quantity. Volume expansion. For solid objects, volume expansion can be expressed as in following equation. Here, V naught is the initial volume, V is the final volume, theta is the temperature difference, gamma is called the volume expansivity. Subjecting gamma, following relationship can be treated. According to this expression, volume expansivity gamma is the fractional change of volume per unit change of temperature. SI units of gamma also per Kelvin, gamma also a dimensionless quantity. We can find a relationship between linear expansivity and area expansivity as follows. Imagine we have a rectangular sheet metal whose lengths are L10 and L20 respectively, and area A0. By increasing the temperature theta degrees of Celsius, the area of the sheet will be expanded to A, whose side lengths will be L1 and L2 respectively. Now, using the linear expansion relationship, we can write following two equations. Here, alpha is the linear expansivity of the same material. Now, by multiplying the equations 1 and 2, since L1, L2 is A and L10 times L20 is A0, we can rewrite this relationship. Since alpha is usually a very small value for materials, alpha squared is even smaller value. Compared to 1 plus 2 alpha squared theta squared is a very small, so that we can neglect. Therefore, neglecting alpha squared theta squared, we can reduce this expression to this relationship. Now, if we compare this relationship with A equals A naught times 1 plus beta theta, we can realize that beta equals 2 alpha. Therefore, area expansivity of a material is 2 times the linear expansivity. Now let's find out the relationship between linear expansivity alpha and volume expansivity gamma. Consider a cuboid whose side lengths are L01, L02 and L03 respectively. If we increase the temperature by theta degrees of Celsius, and volume will expand to V. Now the side lengths of the cuboid will be L1, L2 and L3 respectively. Using the relationship for linear expansion, we can write following three equations. If we multiply these three equations together, we get this relationship. And here, L1, L2, L3 is V, L01, L02, L03 is V naught. Therefore, we can rewrite this relationship as this. By simplifying further, we get this equation. Since alpha is usually a very small value, alpha squared is even smaller value, and alpha cube is further smaller value. Therefore, compared to 1 plus 3 alpha theta, 3 times alpha squared theta squared and alpha cube theta cube are negligibly small. Therefore, we can write this relationship as this. And now, if we compare this equation with V equals V naught times 1 plus gamma theta, we can understand that gamma equals 3 alpha. Which means that volume expansivity of a material is 3 times the linear expansivity. If we consider expansion of liquid, a liquid has to be placed in a container while heating. Heat flows to the liquid through the container walls. Therefore, the container volume also expands, and the level of the liquid will be lower than that would have been if there was no expansion in the container volume. This observed lower expansion of the liquid is known as the apparent expansion of the liquid and is smaller than the real expansion. In other words, real expansion of a liquid is always greater than the apparent expansion. The real expansion is really the apparent expansion plus expansion of container. We can write that relationship as this, where delta VR is the real expansion, delta VA is the apparent expansion, and delta VC is the container expansion. Now, I will manipulate this relationship in order to get a relationship between real expansivity and apparent expansivity of a liquid. However, this proof is not expected to know in case of A-level students. We should keep in mind only this following two expressions where gamma R is the real expansivity of the liquid, gamma A is the apparent expansivity of the liquid, gamma C is the volume expansivity of the container material. We can rewrite the same relationship as this, where alpha is the linear expansivity of the container material. Now we discussed expansion of volume due to temperature rise. However, we know that mass of material does not change with temperature. Therefore, density also changes with temperature. When a given mass of a solid or liquid is heated, variation of density with temperature. When a given mass of a solid or liquid is heated, its volume increases. Accordingly, the density of a solid or a liquid decreases on heating. With increase in temperature, volume increases, so density decreases, and vice versa. V equals V naught times 1 plus gamma theta. Since mass does not change with temperature, we can find out this relationship of change of density with temperature. Anomalous expansion of water. The anomalous expansion of water is specific property of water whereby it expands instead of contract when the temperature decreases from 4 degrees of Celsius to 0 degrees of Celsius. The density becomes less and less as water cools down below 4 degrees of Celsius till freezes at 0 degrees of Celsius. Hydrogen bonds of water molecules are responsible for this behavior. If we graphically represent the change of volume and the change of density of water between the temperature range of 0 degrees to 10 degrees of Celsius, it can be shown as follows. The black line represents the change of volume with temperature, and the red line represents the change of density with temperature. That is the end of the topic expansion.